Today I want to discuss something that I came up with independently and was just curious about the different properties and different kinds of functions you can get. And the idea is that we're going to discuss functions that are always intersecting at a right angle no matter where they intersect, which is kind of a strange idea. We're pretty familiar with this idea with regards to perpendicular lines, and we're going to talk about that, and then we're going to generalize this concept to derivatives, and we're going to show some basic properties that allow us to ask simpler questions than we might otherwise. Then we're going to look at some general cases involving particular combinations of functions, and then we're going to look at some specific examples of functions that we all know and love, and the functions that are perpendicular to those. And you might find out that there are some pretty wacky results. So to start off with, we're going to talk about perpendicular lines. So in the xy plane, lines that intersect at a right angle are called perpendicular or orthogonal, right? They intersect at a right angle, and lines have constant slope, so there's, they could, essentially what I'm saying is I could take this line, I could move it up or down wherever I want, and wherever they intersect, it's always going to be at a 90-degree angle. And so that concept of moving the perpendicular function up and down and always intersecting with the original at a right angle, that's going to be the generalization we want to make. So let's analyze the slope of, let's put the right angle down here. Let's analyze the slope of this line right here, right? It's got some delta x and some delta y. If we call this delta x and this delta y, then we know that the slope of the first line is m equals delta y over delta x, the change in y divided by the change in x. It's the definition of the slope. Now, to get the slope of the perpendicular line, we have to take this thing and turn it sideways, and we end up with this right here. And what you'll notice is the change in x now becomes a vertical component, delta x, and this change in y now becomes the horizontal component that we're still going to call delta y because it's the same number. But notice now the line does not go up, it goes down. So if we wanted to define the slope of this line, we would have to take this amount divided by that amount, but since the y is going down, it must be negative delta x. So we'll call this one m1, the original slope, and we'll call this one m2. It has to be the change in y divided by the change in x, which in this case is negative delta x divided by delta y. But of course this is the negative reciprocal of this. It's the reciprocal, and it's multiplied by negative 1. So this is negative 1 over m1. And that's the basic idea of what we want to generalize today. Because what I'm going to ask you to imagine is that these lines are not our functions that we're discussing. These lines are but tangents to two functions that are intersecting at the same spot where we see a right angle. So you might imagine one curve comes in here, I'll draw it in a different color. You might imagine one curve comes in like blah, 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 and then it is perfectly tangent to that line there, right? And then another curve comes down, blah, 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 and is perfectly tangent to that line there. So these are two functions, and that was terrible. That was, hang on, let me make that look way more 90 degrees. Like that. So what I'm essentially trying to find out is, if I'm given some function that has a certain slope, can I find another function that is always got the perpendicular slope, the negative reciprocal slope is that function. And what that means is that if I take that new function and move it up and down, no matter how much, it will always intersect the original function that I had at a right angle. So given some function that we like or that we're interested in, what function describes, what function has perpendicular or negative reciprocal slope everywhere? So let's investigate that a little bit. So what I'm asking is, instead of just finding lines that are perpendicular, what if the slope of a full, the slope over the whole function is perpendicular to another one? So essentially what I'm saying is we're going to be given f of x, some function f of x that is differentiable. We're going to define a new function that is called f perp, or perpendicular, putting this little perpendicular sign as a subscript. And we're going to define this function such that the derivative of this perpendicular function is simply the negative reciprocal of the derivative of the original function f of x. And what this is saying is we're defining a new function whose slope is the negative reciprocal of the original function's slope, which guarantees that no matter where these two functions intersect, assuming we don't take the perpendicular function and move it left and right, we only move it up and down, we're going to intersect the original function f of x at a right angle, which is the goal. Now, here's a couple of simplifications we can make. If we multiply our function by a, some number, so if we say do a times f of x, then we take the derivative, we get a times f prime of x, then we do the reciprocal, the negative reciprocal, we get -1 over a f prime of x. Notice that this is just a constant times the original expression. This is just 1 over a times the derivative of the perpendicular function of x, right? Because it's just 1 over a times -1 over f prime of x, which is just 1 over a times this. And so when we integrate this to get the perpendicular function, we're going to get just 1 over a times whatever function it is plus a constant. But essentially it's just a constant difference. So if there is some leading term that's being multiplied by a number, we can just divide that number out, because all that's going to happen in the end when we find the perpendicular function is the perpendicular function is going to be scaled down by that same constant. Whatever we multiplied the original function by, we're simply going to be dividing the perpendicular function by that number. And so, first of all, that tells you that that constant can't be 0, because then we would have a vertical line, right? You'll notice that cases where functions have a derivative of 0, it's going to be a bit iffy, and you're going to end up with some very cool pictures. So essentially what I'm saying is we don't need to care about any constants, because it just means we have to divide by that constant at the end. Another thing we don't have to consider is adding constants to our original function, because what happens once we integrate this, once we integrate and get our actual perpendicular function, right, it's going to be some function that we can then add a constant to move it up and down. Now, adding that constant up and down is going to move the point of intersection around where the two functions where they come together. But at that point, it will always be a right angle. If the original function we had also has a constant added to it, that's no different. Adding a constant to this is no different from subtracting that same constant from this function to bring the two together in the same way. So if there's any constants that the original function has, we just don't need to consider them, because A, they're not going to affect the derivative, and B, we can just put any constants with the perpendicular function so that the original one stays put, and this one can just move up and down to change where it intersects. So those were the simplifications that we wanted to make, the properties of this thing. Now let's take a look at some general cases just to see if maybe we can gather all certain types of problems together in one sort of umbrella, and then we don't have to do as much work. What would we have to know to find perpendicular function of the inverse of f? So find the perpendicular function to the inverse of some function f. So we're given f, we're given the inverse of f. Now what do we need to know to find the perpendicular function to the inverse? So, well, we need to take the derivative, that's first, and the derivative of the inverse function of f of x is, you may recall from videos that I've done, it's 1 over f prime of f inverse of x. That's the derivative of the inverse function, and of course the negative reciprocal of that is just negative f prime of f inverse of x. And so if we want to find the function that is perpendicular to the inverse of f, we need to integrate this. So we know therefore that f inverse perpendicular is equal to negative the integral of f prime of f inverse of x dx. Now, this integral is not solvable in general. It's not elementary in general, and we can see that by doing a simple substitution. Let's let u equal the inverse of f, which means that f of u is equal to x, which tells us that dx is equal to f prime of u du. Doing the substitutions, we see that our integral is simply equal to negative the integral of f prime of u, which is f prime of u, and then dx is f prime of u du. So we end up with f prime of u squared du. And in general, integrating the square of some function is not elementary. And so we may be able to find some specific examples in which evaluating this integral is nice and simple, and lots of the ones that we care about, like all of our nice elementary functions, do have nice answers in this way. nice answers. I mean that we can actually express them, though some of them are a bit cumbersome. But the point is that we can't do this in general. Luckily, our functions that we care about are pretty nice. So this is step one. This is the first sort of general case. If we wanted to find the perpendicular function to an inverse, we would need to know how to integrate the square of the derivative of the original function f of x. Not f inverse, but f of x. So that's a requirement. That's necessary if we want to be able to answer that question. So that's maybe formula number one. The next question is, what if we wanted to find the function that's perpendicular to the natural logarithm of a function? So let's say the natural log of f of x, but perpendicular to that. So I'll say like that. That's a little silly looking, but we're gonna see what we need to know to be able to find this. Well, first of all, we have to start with the natural logarithm of a function, and then we need to take the derivative, so we get f prime of x over f of x. That's a pretty basic calculus result. That's just the logarithmic derivative. But then, of course, the negative reciprocal of that is negative f of x over f prime of x. And so if we wanted to find the perpendicular function to the logarithm of some function, we would need to take the integral, the negative integral of f of x over f prime of x. And so as you can see, this is probably also not going to be solvable in general, just because we can't do any nice substitutions. So we just sort of need to hope that our functions are nice enough relative to their derivatives that this integral is solvable. But we'll see we actually end up with probably the nicest examples of functions paired together that are perpendicular to each other using this relationship here, which I will show you in a bit. There's some other questions you might want to ask, like, is there sort of some second perpendicular function? You know what I mean? Sort of like how there's a second derivative or a second integral or something like that. And you can sort of generalize that idea. And essentially what that means is you take some function, you calculate the negative reciprocal of its derivative, and then you take this function and calculate the negative reciprocal of that derivative, which in this case I believe comes out to, well, let's just see, what's the negative reciprocal of this thing, right? The negative reciprocal of the derivative of this function. Well, this is negative f of x to the negative, or negative f prime of x to the negative 1. So if we take the derivative of this, we get negative 1 times negative 1 times f prime to the negative 2. So we get f prime of x to the negative 2. And then we multiply by the derivative of the inner function, which just gives us the second derivative of that. But of course, f prime to the negative 2 is just the same thing as 1 over f prime squared. So we get f double prime of x divided by f prime of x squared. And that looks pretty nice, but remember, we now have to take the negative reciprocal of this thing. And so we end up with negative f prime of x squared over f prime of x. So this is sort of like the second perpendicular thing, because if you integrate this, you're going to get the function that's perpendicular to this. And if you integrate this, you're going to get the function that's always perpendicular to this. And so it's like a layer, levels of functions. And you can also ask yourself these perpendicular differential equations, right? Is there a function that is equal to its negative reciprocal slope? It turns out there is. It's actually the case that f of x is, in this instance, the square root of some number minus 2x. And these functions are always equal to the negative reciprocal of their derivatives. And then if you ask, are there any functions that are equal to the second negative reciprocal of the derivative? And it turns out you actually end up with a very similar function to this one. You end up with some number times the square root of some number plus 2x. So it turns out that the first couple simple examples of take the negative reciprocal of the slope, find the negative reciprocal of that thing's slope, you end up with two very simple answers to those differential equations. This function, I'm sorry, this should have been a minus, but I believe that should have been a minus. I know this one is definitely a minus. I'm not exactly sure about that one, but these could be your homework questions. So if you're fine with solving pretty simple differential equations, then solving this one, finding the function will give you this, and solving f of x equals this will give you this function right here. I tried the next level up by finding the negative reciprocal of the derivative of this thing, and then finding functions that equal that, but I simply could not solve that. In fact, I don't even think Mathematica, I don't even think Wolfram Alpha can. But these are the first couple cases. They're kind of nice. Not anything nearly as useful or pretty as e to the x being its own derivative, or, the trig functions being in a cycle or anything like that, but it's kind of neat. Okay, now that we're done taking a look at things like that, let's talk about specific functional examples, because I think that's probably the most interesting case.